Okay, so we dealt with in the first video on 11.6 the ratio test, and we did a bunch of examples of that. Let's go ahead and talk about the root test. Now, when we're doing these, we need to recognize the similarity between the two. Now remember, the ratio test says this, okay, that if I identify a sub n, I can find an a sub n plus 1. Which is just plugging in n plus 1 for all the n's. The ratio of those two, the limit as n approaches infinity, okay, is going to actually tell me, you got to make sure you get it right, because to get the reciprocal is going to throw off the less than 1 or the greater than 1. So if I have the limit as a sub n plus 1 over a sub n, and that's less than 1, then it's going to be absolutely convergent. Now, like I said, it's not really a big deal to learn absolute convergence. Just every time you see converges absolutely or absolute convergence, just think convergence, okay? If it's greater than 1, if it's a finite number greater than 1, or if it's infinite, in terms of its what it approaches, then it diverges. Unfortunately, this test is inconclusive if the limit actually equals 1. Now this was the ratio test. We did a couple examples of that. The root test is just a different object of the limit, different argument in the limit, but basically the stipulations as to what conclusion you come to are identical. So less than 1, absolutely convergent, greater than 1, are divergent, and equal to 1, inconclusive. Okay, now you've got to remember the absolute value bars in there, because there are alternating series, and that's kind of what the absolute value bars are there sort of to get rid of, so to speak. Okay. One more thing that we actually need to talk about before we actually move on, and this will come in handy in a couple of problems. You simply need to know that the limit as n approaches infinity of the nth root of n is equal to 1, okay, because that will actually pop up, and not all that often, but every once in a while. Now, let's go ahead and start with an example of sigma n is equal to 1 to infinity of, and let's just do an easy one to start out with. Let's do 1 over 2 to the n, okay? Now, that should be relatively easy to see that, okay? But if you want to go ahead and write it, go ahead and write it. Now, this is a simple geometric one, and we ought to be able to tell that it converges just by looking at it, okay? But like I said, this is sort of a Mickey Mouse. This is an introductory training wheel sort of one, so I want to see whether we get the same conclusion when we use the root test, okay? So we know that a sub n is 1/2 to the n, and I know that the limit as n approaches infinity of the nth root. Now, you can either do it under the nth root, or you can simply raise it to the 1 over n power. Those are equivalent, okay? So I have 1 over n, and that is equivalent notationally, because remember, all roots are simply fractional exponents. Oh, by the way, you need absolute value bars around there. Those are the same thing, and you may want to do it this way simply because multiplying exponents is a little bit easier than dealing with radicals. Okay, so what happens here is I have the limit as n approaches infinity. When you're not going to get anything other than positive numbers out of here because you have a positive base, right? And you're multiplying by, basically there's nothing in here that's going to make it negative. It's exponential, okay? And so basically the absolute value bars are kind of window dressing. Once I simplify, I just get down to a constant, and the limit as n approaches infinity of a constant is simply that constant. Now I notice that is less than 1, therefore it is absolutely convergent according to the root test, or just for our purposes, convergent. Okay. Now that should be relatively straightforward. Let's go ahead and look at another one. Let's look at n is equal to 1 to infinity of, let's do that one. N over 2n plus 1 to the n. Okay? So I recognize the fact that my a sub n is n over 2n plus 1 to the nth. And once I set up the root test, what I have here is that. Okay. Now when I multiply those exponents, I'm simply going to get limit as n approaches infinity of n over 2n plus 1. And I can do this by the rigorous method of finding limits at infinity that you learn in calculus and you kind of wonder why. Or you can just harken back to the old Algebra 2 pre-cal way of doing this when you looked at in behavior asymptotes for rational functions. This winds up being the same degree in the numerator and denominator. So the rule is that we look for the ratio of the leading coefficients. This is also 1/2 less than 1, and therefore this is convergent. Okay? Now, let's go ahead and do one that is maybe a little bit more robust. How about n is equal to 1 to infinity of n to the n over 3, 1 plus 3n. Okay? And there are, 1,000 different ones like this in every single textbook, so they just sort of mix up the numbers in there. It's 2 to the 1 plus 5n or whatever on the denominator, but they all sort of work similarly. Okay, I know that that means that my a sub n, and I don't really have to change the form, though I could turn this into 3 to the 3n times 3 by using my rules of exponents. I could even further, if I wanted to, let's go ahead and put it down here. I could go ahead and resolve the 3 cubed and just make it 27 to the n times 3. And that means that when I take the limit as n approaches infinity, okay, excuse me, of the absolute value of n to the n over 27 to the n times 3, and then I want to raise that to the 1 over n, I can bring that out, right? Anytime I have something like this, I can bring it out. But I'm just going to go ahead and leave it in there, okay? And I recognize the fact that I have the limit as n approaches infinity, okay? And once I actually distribute all this around, you wind up having n in the numerator, 27 in the denominator, and 3 to the 1 over n. Now here's the thing. When n goes to infinity, what happens to 1 over n? 1 over n goes to 0, okay? So this quantity right here is approaching 3 to the 0. As that's approaching 3 to the 0, this numerator is going to positive infinity. Okay? And so what I have here is I have infinity over 27, because 3 to the 0 is just 1. And therefore this winds up being infinity. That winds up being greater than 1. It doesn't have to be a finite number greater than 1. It can be a finite or infinite number greater than 1, meaning that it can be approaching 2, it can be approaching infinity. It doesn't really matter. It's greater than 1, and therefore this is divergent by the root test. Okay? Now, let's go ahead and move on to another example. Yeah, I think that's probably a good one. Okay, now my a sub n winds up being what? Well, my a sub n is negative 12 to the n over n. The absolute value of a sub n is going to be a little bit different, because the whole absolute value thing is there to get rid of that back and forthness that the alternating series have. Okay, so if we do the limit as n approaches infinity of negative 12 to the n over n to the 1 over n, we're going to get the limit as n approaches infinity of 12. The absolute value bars basically make that negative evaporate after you've applied the 1 over n to that exponent right there. And I get n to the 1/nth, or the nth root of n. Remember that the limit as n approaches infinity of that quantity, I told you right at the beginning, is equal to 1, and therefore this limit is 12. That is greater than 1, and therefore that is divergent. Now, should we have guessed that on these last two? Because remember, we want to have sort of that gut instinct when we get into a problem like this of what's probably going to happen. This is exponential in the denominator, but that's a hyperfunction in the numerator, and that's more aggressive. So we're assuming that if the numerator is a more aggressive class of function, it's going to be increasing much faster than the denominator, and therefore it's sort of going to break away and cause it to go to infinity. Well, the same thing here in the denominator, despite the fact that that's negative right there, okay? And actually you can break that out and, actually turn it into two separate. That's -1, which is the oscillating part of it, and then 12 to the n is just the sort of numerical part of it, and therefore the absolute value of a sub n is just this portion right here. But that's an exponential in the numerator and a linear in the denominator. We should have expected it to be divergent. So even though you have to actually show all of this analytically, there's no reason why you shouldn't, even though you have to show it analytically, there's no reason why you shouldn't stop and think before you start on the problem and get a good sort of hunch as to what exactly is going to be going on once you sort of get into the mix of it, okay? Let's do another example. And like I said, we're not going to spend a whole lot of time on the root test. I just want to do a couple of examples, a nice sort of selection from what's available, so that you can see it, you know it's there, you know a couple of the tricks of the trade. But here's the thing. You so rarely use it. The ratio test is really the big payoff of this particular section, because when we get to power series, it has a role. It has another role there in terms of being able to talk about convergence of those power series, those infinite polynomials that I told you about. Now you know that your a sub n is going to be, well, let's go ahead and, we can break it apart. You don't have to break it apart. It depends on whether it actually helps you to see it in your mind's eye. This becomes n times n to the -3n. And you could resolve this to 16 to the n down here in the denominator. It doesn't really matter. So let's go ahead and do the limit as n approaches infinity of the nth root. So like we've done before, we're just going to raise it to the 1 over n of the absolute value of n times n to the -3n over 16 to the n, and we're going to raise that to the 1 over n. Once we actually sort of push that into all the factors in that rational expression, you're going to get n to the 1 over n, or the nth root of n, times n to the -3 over 16. Okay, well, let's simplify that just a little bit more and put it into terms that we're actually comfortable with. That's the nth root of n over n cubed times 16. Okay, well, if the denominator is going to infinity, which we know that it is, okay, because basically as n goes to infinity, this goes to 1, like we've already talked about, this goes to infinity, and this of course goes to 16 because it's a constant, right? So basically we have something that's getting rather stable in terms of its value in the numerator. It's going to 1, and the denominator is just exploding, and therefore this winds up being 0. 0 happens to be less than 1. Therefore that is a convergent series by the root test. Okay, and there are a couple other different varieties of this. The root test is sort of a small player in all of this, so we're going to go ahead and stop here. If you have additional questions on the root test, or the ratio test for that matter, make sure you email me and I will try to provide clarification, additional examples, whatever. But from here we're going to move on to 11.7. 11.7 is where we bring all of the tests that we've learned, both the ones that we've reviewed like the geometric series test in 11.2, along with the new ones that we've learned, the integral test, the comparison tests, the alternating series test, and the ratio and the root test. And we bring them together, and if we are given just a variety of questions, we not only have to tell convergence versus divergence, but we have to be the one to choose the particular test that we use. And so to practice those strategies is a pretty good idea, and that's kind of the reason why Stewart actually added an additional section in his book that does not cover any particular strategy, but actually is a summary of all of them. So we have that to look forward to in 11.7. Once we're done with 11.7, we're going to move on to power series and Taylor and Maclaurin series. So we're going to be moving away from the numerical series that we've been doing, and we'll be moving towards variable series, or what are often look like infinite polynomials. So we have that to look forward to. If you have any questions, as always, please do email me. Bye.